Assalamualaikum warahmatullahi wabarakatuh.
Waalaikumsalam warahmatullahi wabarakatuh.
Good afternoon, ladies and gentlemen. Again, thanks to join in the first collaboration event between ISPG, IAGI, and IATMI. Today we have a production enhancement using AiRP, Artificial Intelligence Response Prioritization. So I think this is a good topic, a good knowledge for all, to IATMI and to IAGI, and to all participants here. So before we are going to the next presentation, I would like to invite a representative from IATMI, which is Pak Hadi Ismoyo, as a secretary from IATMI to give an opening speech. Please, Pak Hadi.
Thank you, Pak Julianta. Bismillahirrahmanirrahim. Assalamualaikum warahmatullahi wabarakatuh. Salam sejahtera bagi kita semua. All of the participants from the oil and gas professional in Indonesia and outside, thank you. This is good start for collaboration between all the association, including IAGI, ISPG, and also IATMI, to have the good and innovation on the lot of things to increase our production, because we have very ambitious target 1 million barrel a day. So we have to start thinking to have the not thinking vertically only, but also laterally. How do we strategize among association to have the good innovation to increase production in our field? Topic that they present today by Pak Tonio, Pak Mirsa, is very good topic actually, because this is give us fast decision on the field. I also have experience on my field that I I talked before this meeting. Look like that I have the lose production 5,000 to 7,000 a day because of we need to anticipate some of the skill problem. Basically, skill problem is we have a lot of data before that, and also we have downhole kit pressure and temperature to see what kind of the behavior every day. So we have to have the good decision in the beginning, so not too late to anticipate this problem. And right now we lose gain because the production decline very fast. So I hope from this seminar we have a lot of experience, that knowledge that we can solve from Pak Tony or Pak Mirsa to apply for our field. Even single field, we have to looking for the opportunity to increase the production. Even the marginal field, even the idle field, or discovery and develop, we have to looking for that to help the government to increase the production. That's what I have. I hope you enjoy with the seminar. Thank you. Back to Pak Julianta.
Okay, thank you, Pak Hadi, for the opening speech. And before we continue, I would like to introduce our moderator today, which is Mas Ode. I call him Igede Odesia Satya. So this is the profile from Mas Ode. Currently working as a junior real-time support engineer at Petrolink Services Indonesia. And before that, he was studied in UPN Veteran Yogyakarta, Bachelor Degree of Petroleum Engineering, and currently active as the board of SP Java Indonesia section from 2021 until now. Many achievement has been produced by him. The latest one is a publication in Beijing, China, 2021, in the International Symposium on Water, Ecology, and Environment. First runner-up International Paper Competition at OJIP 2021. Champion of International Paper Poster Competition at IPFest, and top 10 finalists in IATMI SFPC 2020. Without any further ado, I would like to pass on this session to Mas Ode to lead the discussion and introduce the speaker. Please, Mas Ode.
Okay, thank you, Mr. Julianta, for the introduction. Okay, let me introduce again. My name is Igede Odyssia, and here will be a moderator for today's session. So as explained before from the Mr. Julianta, for today's session we have the topic with the theme, which is the production enhancement using AiRP or artificial intelligence response prioritization. The abstract or overview of today's topic you can see also on the screen, but currently following the field challenges and looking for a platform that can address the almost in other in aspect in oil and gas industry, such as enhanced production capabilities and artificial require an AI response prioritization. But then the reality is today's response to the well event, it takes a long time to identify and diagnose them. Hence, the automated filter system is needed to be a solution for this problem. And for today's topic, the Schlumberger Sensia AI Response Prioritization will be a solution for the problem. This platform is an intelligent store for all the accumulated knowledge that automated event detection engine framework processes in ESP, starting from the downhole surface and electrical sensor data to detect and identify the potential harmful patterns by the real-time surveillance. This will reduce the false or unnecessary alarms to bear a minimum with the optimum balance of domain understanding and machine learning. The optimization of the lifting and the cost and minimize the cost will be another advantage. This platform is expected can extend to the other artificial lift such as SRP, gas lift, PCP, and other production optimization workflows. So for today's session, it should be given by the Mr. Tony Brito or the representative Mr. Misra from the Schlumberger. And for this is the short profile of our speaker today. He is the Senior Digital Alliance Manager at Schlumberger and graduated in business from the Universidad Central de Venezuela in Caracas with graduate studies in artificial lift production optimization. Mr. Brito has been working in oil and gas industry in more than 25 years and has participated in the multiple successful digital oil field projects in worldwide with a special focus on digital oil field infrastructure and information systems. So next, before we go to the presentation session, I will read the rules for the presentation session. So please ensure for all participants to turn off your microphone during the presentation sessions, and the material will be given by the speakers today for about 1 hour, and then followed by the question and answer sessions. And you can ask the question in the Q&A sessions. So without further ado, for the material given from the speakers, so for the representative from the Schlumberger, time and place is yours. Okay, sir. Yeah.
Okay, I just want to make sure you can see and hear my screen and myself.
Yes, sir. We already see your screens and hear your voice clearly.
Okay, excellent. So thank you everybody for your introduction and giving this opportunity to present. So we would first of all, appreciate your patience. Tony couldn't able to join because of the technical glitch, and we deeply apologize for that. He would try and see if he can join over phone, but I would try my best to fill in for Tony Brito in this session. So first of all, as you know, this topic is very, very interesting and relevant topic, and Schlumberger and Sensia has joined together in this journey with all of you to see how we can prioritize the low-hanging fruits in case of production optimization through artificial lift. And because artificial lift itself is a huge topic, we can't really cover all of those. So what we are trying to do is we are trying to make sense with ESP first. And if you really find this topic interesting, then later on we can have subsequent sessions with soccer rod pump, gas lift, PCP, etc. Let's deep dive into it. As we all know, the ability to prioritize the relative importance of event lies in people, not programs. So historically, all the prioritization has been done by either our operator in the field or by our technical expertise within the team. There is no system that is able to capture expert knowledge from recorded time series and events to support operation management. Slow loop system offer hit and miss analytics and insight of monitoring and the alarm. So whenever you are running a production surveillance, you are too dependent on those human factors to detect and tell you, okay, the production is running okay, it's not running okay, what are the cause, what are the side effects of that, and what mitigation measure we can take. So field engineer can see these events, but as the number of events increase, they need to find difficulties to qualify and quickly respond what kind of mitigation measure we need to take. So without the full picture of failure prediction, it is impossible to optimize our wells. So a little bit of background of what is the relationship between Schlumberger, Sensia, and how this whole piece is coming together. So as you know, we created, perhaps many of you already know it, we created this joint venture from Schlumberger in collaboration with Rockwell, and we name it as Sensia to address mostly the digital portfolio and enhance the customer experience into production optimization. So Sensia does and shadow the greater Schlumberger organization as a team where we are taking care of specific production surveillances as well as surface wellhead digitization initiative. And that comes with a lot of pedigree from Allen Bradley Rockwell, power of automation, embedded with the oil and gas petrotechnical expertise from Schlumberger. So whatever you are taking a look at with Sensia has greatest contribution both from Schlumberger and Rockwell organization. So where we operate, just a very brief background about what we do. So we automate the process, the workflows, to enhance the safety, the health and safety. You would see in a moment how automating ESP will also allow the maintenance and operation crew to mobilize less and not to visit site frequently, which will give you saving in OPEX cost. It will give you a lot of greenhouse reduction in greenhouse gas footprint, and also reduce exposure for COVID situation, which is undergoing now. The second thing is measurement. Measurement has been contributed by Schlumberger to this joint venture coming from Cameron, where we are taking care about flow, pressure measurement, all the things which is going in and around in a surface facility. And digital solution, which is this AiRP session is for, taking care of the automated workflow specific to production workflows, right? Like artificial lift, ESP surveillance, and lift surveillance is one of them. So what we are going to cover in today's agenda, which is approximately 60 minutes, but we would try to condense it down to, let's say, 40-45 minutes to take your question. We'll start with the ESP automation and health management, like how do you know your ESP functionality is going well? So from the electrical signature, we'll take a look at initially, and then gradually we'll focus our SIP to prioritize based on those symptoms. It's just like an analogy of a person. If you go to a diagnostic to a doctor, he first checks your physical attribute, your pathology attribute, and then try to understand what kind of issue is that, and later on prioritize. So we'll look at the prioritization. How do we diagnose and prioritize? Then what are the electrical signature? How can we take the electrical signature of our equipment, not very sophisticated equipment, downhole, maybe from the surface, whatever we have, it can be a variable speed drive, it can be a pump frequency or a speed, and how that can lead to an interpretation for event detection. And gradually we will go to artificial intelligence. Well, predictive model analysis and control action can be taken for that specific ESP in order to avoid failure such as ESP itself, or gas lock issues, or pump off issues, or maybe some of the sand production issues which you have. And finally, I'll talk a little bit about this new digital twin. It's a fancy word, but we would try to give you some perspective how digital twin can play a very vital role on these AiRP solution. And finally, we'll take some of your question and answer. If I'm running fast, please let me know. I will slow it down, sir. Okay. So as we always do in Schlumberger, we always start with a safety moment. So as most of us now, in Indonesia is seeing through this phase of lockdown, it's important we reiterate some of the safety moments with relation to kitchen hazard. So the topic today is very close to my heart because I have an 8-year-old son who unfortunately had to go to kitchen for a bread to toast, which we did it for him. It was kept under the toaster, but we forgot that the toaster was hot, and the guy went there and he burnt his finger. So sometimes, being parents, we take things as granted because we think the kids already know the toaster is hot and he won't open it. But believe me or not, my 8-year-old son did that despite he knows this is a toaster. So it's very important that we take care of these kitchen hazards, especially in the work from home environment where we are running meetings. We would not let our kid go to the kitchen and do things by them. And then storing utensils and sharp objects like knife in proper place so that these kids do not get access if they want. And then the electrical cords. Whenever you are running a laptop or a workstation, let's make sure all the electrical cords are properly socketed and they're not laying down so that any of the infant or babies who is crawling would impact by that. So that finishes the safety moment. And now we will shift our focus to today's topic, which is AiRP for ESP automation and its health management, right? So first of all, what we did is we split into tried themes. There are 2 tried themes, right? And these tried themes are based on the electrical signature or automatic event detection. We call it AED. That comes through the equipment itself. And some of those also comes from the reservoir or the well behavior, right? So when you go for a ESP optimization, you look the physical piece, which is the equipment, and then you look at the holistic piece, which is your nature, which is the reservoir. So the challenges which we got, the reservoir challenge is basically sand and scale production, and then pump wear and tear. And the physical challenge on the equipment side is manage the alarms, because in a practical world, when we are running an equipment and that equipment is giving you hundreds and hundreds of alarms, somebody needs to see it, somebody needs to manage it. And more importantly, after seeing and managing, that person should come out with some decision. So historically, ESP surveillance is done in a way where your petrotechnical domain and operation maintenance domain has a very close collaboration. But as you all know, oil prices are dancing around all year. We have challenge over cutting down cost. We have challenges over training people. We have challenges over sending people at site to actually physically check and manage because of COVID. So these are not practically possible in today's time. And then you have wellbore changes, which is out of our control, where you have non-homogeneous gas flows causing damages, especially for a low flow events. And then you come with operational challenges such as efficiency, people trainings, and finally the intervention, which is causing by your deferred production. So if you have a deferred production due to an ESP failure, or you don't take action proper time, then your whole production cycle goes down, right? So under this advisor project, we have two different scope of work. One is focused on automation, which is basically the ESP piece. And then what we are trying to focus is we have ranges of market with high volume land to offshore application, where this is focused on particular ESP health management. And the other game changing piece of technology is focused around the failure prediction. So one way you manage your ESP, the other way you diagnose the ESP information in such a way that it gives you certain decision-making ability. And that is more critical for all of you who is gathering here and spending your time, quality time to understand this technology. So let me cover the automation piece first, and then we deep dive into the analytical piece, which is the failure prediction piece. So around automation, we are working on automated event detection of the ESP to automatically flag an adverse event that could damage your ESP and shorten its runtime. Okay, if you're damaging your ESP and shortening your runtime, what is the problem? The problem is your production. You are losing production due to the downtime of the ESP pump. This algorithm being worked on will acquire a certain minimum level of measurement to be available in the field, such as type 1 downhole sensor and wellhead pressure sensor. Okay, as the algorithm are refined and improved, we will able to send these out over the air to our latest IoT device, which will be installed along with the ESP pump at site. And as a result, you will get automatic event detection system. Those are going to show you only the alarms which is matters for you, and it will process all other information at the background and not able to give you unnecessary bugging or triggers or alarms, which is not important. For instance, if you're getting a high pressure alarm every 5 minutes, the operator doesn't bother because that high pressure alarm may not be of greater importance. But let's say if you have a sand production or a pump off, the operator is more interested. So the AED, the automatic event detection system, will manage that alarm profile, and make it qualitative rather than quantitative. That's the objective of the first piece. The second automation piece is about the failure protection. So you have the information about this alarm. Now what you do is you take the electrical signature and come out with a lot of ESP curves, which is embedded due to the historical Schlumberger background for Kudu pumps and many other pumps, where we know the electrical signature, we know the pump curve analysis, and then we can link it that with the basis of physics-based model to predict if this is the voltage, this is the current. I'm giving you a very vague example or a simplified example to make you understand. Then maybe I have a, let's say, increase in temperature and vibration is leading to a sand problem. So then the mitigation measure would automatically come to slow down your pump speed. So these are the attributes we get overall from this topic. Now, let's see how prioritization takes place today, right? In all these ESP well, including in Indonesia. And then we will see how we can improvise from today to tomorrow, right? So today, the ability to prioritize the relative importance of event lies in people, not in program. And that is where we have, slow loop system, where it is a hit or miss because it's run by field engineer and they can see the event. But as the number of events increases, it is relatively difficult for that field engineer to qualify and quickly take action to be able to protect your ESP and production. Okay. And this is how it is done. You have, if you see my pointer, you have the wellhead, you have the ESP and their relative VFD drives. If it is offshore or onshore, depending on the communication, either they go to a radio or to a satellite. It goes down to a data surveillance center where you have production guys sitting, operation guys sitting, and they would take a look at it, typically 2 to 3 or 4 guys depending on how many wells, and then they decide it. And this is not a very efficient way of doing things, especially in today's time when you really need some intelligence to tell you what are your prioritized well, because you don't want to focus on 100 wells. If you want to see your cash cows. So the system will identify the cash cows and allow you to focus on those good candidates. Okay. Now, how this is possible? How we can, filter the data and complement your engineer, right? To be able to make them better decision maker and not to spend their time looking at alarms and looking at, what is the color code of the graphs coming, etc., etc. So it's a very simple example. If you look at Apollo 11 or those missions, the spaceship, this is the spaceship example, right? The spaceship would have maybe thousands of switchboard and a control system. Then you have the latest shuttle model from NASA, where you have mixture of buttons as well as graph. And finally, you have Elon Musk launching SpaceX with the Dragon, where you don't have almost very limited switches. Everything is touchscreen and self-monitor. Now, how this transpires? This is transpired because of the intelligence which we are making this system today to be able to recognize some basic functionalities, and we keep on replacing them and improvise. The AiRP system or the Cortex-system is similar to this journey. When we have engineers sitting around and watching all the alarms, 24/7, to a system which takes care of the basic surveillance and advanced surveillance piece, and give the time the production engineer to focus on the core issues, not on watching day in, day out functions. It's managed by this platform. So it's actually taking away a lot of load from the existing people and collaborate and complement that. It's not replacing, but it's complementing that so that they can focus on more qualitative tasks. Okay, I hope it's making sense up to this point. Now, reliable failure prediction requires accurate account of operating event history, right? That history is important. Otherwise, how do you know if my pump are going to fail? You need to have their voltage, their current, all the data. And crucially, you need to know time and date and context of the event. Yet disconnected system and data source make it almost impossible to capture the full picture of the event that is occurring day in, day out in thousands of ESP wells within around Indonesia. So AiRP is a fully integrated system that automatically captures, saves, and analyzes this information in real time. I would stress the word real time because it is important. If you don't capture in real time, you cannot able to detect and avoid a failure. Avoiding a failure can give you hundreds of dollars because of deferred gas production. Automatic prioritization and powerful visualization enable more focused operator attention, real-time insights, and closed-loop control. Detecting event is fine, but what action you are taking? Currently, if your guys are sitting in control room, they have to call somebody in the SCADA or somebody in the platform or somebody in the well pad to take action. However, this platform can take some basic workflow based decisions and action, okay, on behalf of your guy. Because if your engineer is out today, Friday, 3 o'clock, if he's out from the office, he's only going to come back on Monday morning. If something happens to the ESP, nobody is there to take care, or maybe some emergency, control room is going to take over. Now we have to come out from that thinking to make sure if there is any basic problem in the ESP during the weekend, the system itself should run and it should make sure the ESP is continue till the time the production engineer comes back on the Monday morning. Once he comes back on the Monday morning, he can always override the decision from the system and say, this is the best, but your pump has not failed. So that is the value you are getting out of this system in terms of maintaining your production and extending the ESP run life. Because you can avoid ESP fail, then your run life is going to increase. Remember, ESP only fails if you have some adverse like pump off conditions or gas lock condition, and it fails within half a minute to 1 minute. So failing an ESP takes fraction of a second. That's why you need this kind of system which protects your ESP and it gives you advanced production, right? And the maintenance of the ESP is also you need to consider. If your ESP fails, you not only it's ESP cost, the maintenance cost, the guy who is traveling to the site to replace that, that's also something very important. So now take a look at the architecture, right? How the architecture plays out. So basically it addresses cloud platform or an on-prem platform. So you can install this surveillance system into your existing SCADA platform or a workstation nearby to SCADA, or you can install this in a dedicated surveillance or a petroleum workstation, and this can be at cloud. And if you have issues on cloud, we can give you an on-prem solution. So the challenges it addresses is basically production optimization to reduce your expenditure for ESP failure. You can scale up to today you're using 10 ESP. You can easily go all the way up to 1000 ESP, no problem. This system is an absolute scalable system. The most important thing is domain expertise. And that is why Schlumberger comes into picture, because you know how much experience Schlumberger got into both the physical piece of ESP as well as the surveillance piece of the ESP. So that is why the SCADA system, if you look at, either it will make or break. Like anything happens, SCADA system will shut down. But in ESP, can you afford to shut down? No, because you need to run that to maintain your production. So that is where you cannot use a conventional SCADA system for an exclusive petroleum domain expertise ESP platform like this. So that is why we are different. We are not a conventional surveillance company. We are doing everything based on the petroleum domain workflow. And that could lead to a powerful surveillance, such as diagnostic capability, event triggers, etc., etc. Okay. Now let's shift our focus. You must be wondering, okay, you're telling all this, but tell us how you detect and diagnose these platforms, right? So what are the issues events normally we get from ESP, right? Sand and scale issue, which we get from the event, slugging issue or gas lock issue, right? Or pump off issues. Then you have automated startup or misrun operation issues sometimes, and you can see the electrical signature of all these issues. So what we do in our pursuit for a longer lasting and more robust ESP installation, we have seen tremendous benefit from diagnostic and control capability of an experienced surveillance team. Okay, that is coming from the people, by the way. We believe the next frontier of the ESP operation is going to be automation of surveillance activity through machine learning. Why? Because we are developing a system called Cortex, part of the Lift IQ family, which is the traditional Schlumberger platform, where the Cortex hardware consisted of industrial computer and advanced high-speed sensors that enables rapid assessment and response to condition in the field. Additionally, these systems communicate with the operator somewhere in the control room, which will do the surveillance and remote monitoring over an air update and ensure access to latest detection algorithm. There are multiple threats to your ESP system which can be mitigated, right? And you can see glass slugging and sand detection, etc. But detection the system swiftly can identify the event before they occur. That is the point. We are not letting the event to happen, or even if they happen, there are some mitigation measure, right? So an ESP system is mostly vulnerable to misoperation during startup. That is where most of the ESP pump fails, right? So to improve consistency, reliability during startup, what do? We are developing the capability to completely automate the startup process rather than working from a predetermined startup procedure. And the Cortex will actively manage the speed, the torque, and the back pressure on the ESP system while monitoring changes in the annulus and discharge of the tubing pressure, temperature, etc. This ensures the smoothest possible delivery to the fluid to the surface while minimizing damaging pressure variance at the ESP and the reservoir. Okay, so this is how we detect. So this is not magic, this is actually physics and science, right? And finally, the electrical signature which you are getting from vibration, temperature, pressure, frequency, speed, it provides us opportunity to improve power quality to minimize electrical stress on the ESP system. Okay. Additionally, we have capability to detect deterioration of the motor condition, because you study the hysteresis loss from the induction motors, right? The eddy current loss, the copper loss, all these stuffs you monitor. And the pump health through the analysis of high frequency signal returning from the motor, whether you are getting harmonics. We'll see in a moment how harmonics can play a very big role detecting the ESP is operating within the band or not. And in future, this data-driven model will help us track ESP wear and tear and predict failure, enabling our ultimate goal by reducing deferred production due to workover planning related constraints, right? So I hope the message is very clear how this has been done. Now, as I promised, we are going to take a look at the harmonics. This is a North American well example. By the way, this is from a geothermal example, right? Just to give you a perspective. We computed the quality indicators of current and voltage, right? So what you do is you detect your current, you detect your voltage, and what you call is the total harmonics distortion, right? If you get repeated harmonics, sorry for my tiny graph, but you can see there is a repeated harmonics coming from the pump, right? What does it mean? It means there is a consistent problem causing these high spike of harmonics coming, which is we call a 5th grade or 7th grade harmonics. Okay, if you detect this, or the system detects this, then it knows my current draw is more. When the current draw is more, then obviously I'm either having a pump off issue because there is not enough production fluid, so I'm running at a higher speed. So what you do immediately, then the system detects this and slows down the speed of the motor so that the harmonics is reduced to a tolerable limit. Okay, so if you look at the drive configuration and a program and the event has a pre-programmed total harmonic distortion, the drive is operated by an open loop vector control, which is OLBC. That will bring down the pump speed to mitigate that gas lock situation. So this is a live example where our customers are very happy with the performance of the system. And then you can take other physical piece to integrate, such as the downhole gauge. If you don't have downhole gauge, fine, we can still manage with some surface equipment such as wellhead pressure, temperature, choke, surface choke, and the variable speed drive, VSDs. So what we do is we do have protectors, that is isolates motors from wellbore fluid, consist of a volume of pressure compensated motor oil. So through this combination of the electrical signature and surface downhole gauges, you can further automate and translate, because if you want to speed down the choke, you need this, speed down the motor, you need this choke, right? So these are the critical element for mitigation measure. Detecting the event is fine, but mitigation measure at site. Remember that Friday afternoon story when the guy left the office and coming back on the Monday? So these are the critical elements which is going to control your flow of the wells automatically, even if there is nobody looking after these wells live. Okay, now we will little bit deep dive into electrical signature analysis, because this is important, that how much critical is electrical signatures. And believe me or not, these electrical signatures are already there in the ESP platform for many years, but nobody really took the pain to get these data to use and get decision out of it. So the AiRP platform actually does it for the first time. So what we are doing here is perform signal processing in both frequency and time domain. Remember, we have all this data, variable speed drive data, you have vibration data, all are timestamped, right? So what we have done is we have done the fast Fourier transform, FFT, as you know, it's a mathematical function, to obtain signature of interest. You can have multiple signature, frequency increasing, speed decreasing. But what is important is to obtain the signature of interest and other derived parameter that can be useful for condition monitoring. Okay, so condition monitoring of the process, which is coming out, in this case can be your hydrocarbon production. Also, the condition monitoring of the equipment, such as, first of all, the vibration. If the pump is vibrating much, as you can see, it's increasing. What does it mean? Either it has a throttling impact, or you have more sand production, or something which is not smooth, right? So then you validate that with the amplitude modulation of the current which is coming in. So if you see there is a vibration, peak to peak voltage is quite significant, you cross check that back with your current, and you see your current is drawing when the vibration is increasing, and your current is dropping once the vibration drops. So that's validates all this happening at the background automatically. Okay, and then finally you detect it and then take mitigation measure, and this can be applied to many problems. This is not just one problem to vibration. This could be sand, this could be gas log. Now you detect the event. Now how do you take action? All this is fine. Now you understand, we detect the event, we have so many problems, we know all the problems. What action the system takes, how it can help those guys sitting in the production surveillance and complement them, right? So the automatic event detection system, or AED engine, begins by considering real-time data from the field, whatever we discussed so far, right? It captures all the real-time data, pump, pressure, temperature, vibration, speed from the VSD, etc. It takes bad lubrication. It analyzes whether this is due to this bad lubrication, heat rise, or vibration. And that is possible because what it makes the system unique is ability to understand the physical property of the system. Initially, the engine considers the quality of the data which is received. And that quality validation I have shown you in the previous slide. How do you validate there is a vibration? There are multiple checks, right? It is doing to validate that condition. And then the engine can discriminate whether variability is due to the transmission noise, because sometimes you might have a noise from a three-phase connection. It can happen, or it could have several other issues which is coming downhole, or to physical fluctuations such as gas production. And additionally, the engine is able to identify whether the data quality is good and bad, whether the sensors are functioning properly. As an example, a reading which is previously varied by small amount, let's say a pressure is varied from 500 psi to 505 psi, but becomes fixed on a single value. Maybe it's an example of a stuck gauge. So if it is stuck on 505 and not varying much, then the system will flag, hey, I have a failed transducer. Whether it is pressure, whether it is flow, whether it is vibration, doesn't matter. Okay, these sorts of insight actually enables the AD engine, okay, to adjust itself. And the alarm threshold and event definition can change in response to change data variation. And the sensor which is failed or begin to read erratical readings, okay, because of so many other issues, are clearly identified to the operator. So currently the operator doesn't know whether that reading which is coming from the gauges, from the vibration, from the speed, whether that is good or bad. So the system will flag you whether this data quality is good or bad, or whether to trust that reading which is coming from the devices. That is another very good ability. You must be wondering why I'm going to use that. Because if you are using a ESP well for a prolonged period, let's say for 2 years or 3 years, you never know the performance of this equipment. And that is where this data quality and validation issue comes into picture. And the next key capability of the engine's ability to see the difference between the operational changes and the reservoir changes. Okay, because you have data of, let's say, last 1 year of the operation and reservoir. If the operation is changing radically, what does it suggest? Take a look at our reservoir. Let's see what's changing, because we must not see this much of change. Earlier, you don't see change because you are seeing only alarms. Nobody is telling those alarms are leading to reservoir change. But now your AD is giving you insightful information why you should take a look at reservoir. As an example, the engine understands that increased pump speed will also increase discharge pressure. Okay, what does it mean? This means that the operator to make changes without worrying about setting to new high-low alarm, right? High-low alarm threshold. With an understanding of the dynamic baseline for each well, the engine is able to identify event and determine their severity. How severe is that in terms of production, in terms of maintenance, in terms of drawing attention physically by a petroleum or a surveillance team member? And then it raises a pre-classified alarm to the operator saying, hey guy, I think this could be due to a heat rise. Please take a look at it. Okay, instead of sending, oh, my pump speed is increased, this is just an alarm. No, it flags that pump speed increase with an increase in temperature and tells the guy there is a heat rise. So for the guy who is going to take some action, it's easier for him to quickly validate the workflow and go back straight to the action rather than, you know, checking it, sitting down, analyzing, and then at the end of the day, you lose production time. By the time he does it, the pump is already failed. So what it does, it increase it will increase the frequency or decrease the frequency. By the time the guy comes back to the system automatically takes the root cause analysis. It adjusts to choke depending on whether it's a sand issue or a gas lock issue. It checks the inlet valve line, or vice versa, as I said, increase or decrease frequency. The remedial action is already there. By the time the guy really comes out for some other action, the system itself avoid the pump failure. So that is the beauty of the automatic event detection system, the action which is taken. Now we have seen different scenarios. Let's shift our focus to pump off and recovery, right? So applying the previous startup practice, that is what we do is we ramp up our pump initially, let's say up to 50, 51 hertz, okay? a pump off condition was then raised, right? The automation, this is a live example from one of our sites, by the way, right? So if you see, we started smoothly and then raised to 51 hertz for a pump off condition was raised to the system. And then the AED engine detects it. The automation began to take appropriate action to decrease the speed. So if you see, the speed of the pump has initially increased and then slowly it is being decreased, okay, to adjust the choke, okay, to close the choke until the severity started dropping. Eventually that eliminates the event, because if you drop the speed and the close the choke, then ultimately you are not running at 51 hertz. Ultimately that is going to come and stabilize. And this is how you actually avoid pump off, which is a very severe cause of your ESP failure. ESP doesn't fail when it's running. ESP often fails once you start up. That is where ESP fails. And it takes, if you look at the time, this is the time, by the way, I think it's in minutes. So this is 20.5, 20 minutes and 5 minutes. And then it can cause 1 more minute to fail the pump if you don't take action at that very moment. So these vertical lines are due to the situation reaching the boundaries between the operating limit and the excessive limit. Once the PO was truly handled, or the pump off is truly handled, the diagnostic switch briefly goes back to the to the operating limit, leading to one raised step for the feed. So it gradually then increases the speed once this is stabilized. So this is an automatic workflow. You increase the speed the moment you see the electrical signature is going beyond the band, it reduces the speed, and then gradually it is stabilized. So this is a classic example how AiRP can eliminate any pump off issue. Then another issue, insufficient lift. Okay, and this can happen in low flowing wells, especially depleting wells with low pressure wells, tight reservoir, sometimes heavy oil. This is a very common cause for those kind of wells. So how the engine responds, let's see, right? So we are in a process of an action of walk back. Okay, what is walk back? It means it takes a small step towards target set point. Okay, so let's say you have a target production limit, or at this speed, if you run the pump, you have the optimum production. In the process of that, a brief insufficient lift was triggered, and that could be due to the motor temperature. It could be due to the various reason down in the subsurface, right? And the walk back was disabled. Okay, followed by the event recovery action. Okay, how do you manage that? Either you manage it by increased frequency or by a step. Now, as you know, there is a insufficient lift. Instead of a long wait, or an alarm is triggered and somebody tells you what to do, the system works itself. So how does it work? So first of all, if you see, you are under, this is your baseline, the green is the baseline at which you should be producing. And then suddenly you start up and you see your production is not as per the baseline, it is depleting, right? Ideally, this can create serious issue, both from a production perspective, from the pump perspective, and maintenance perspective. But then the AED engine swiftly detects the issue. When it falls down the production, it swiftly detects, hey, there is a motor temperature rise. That's why probably there could be a similar issue. The speed is reducing. So what it does, it takes the pulse width modulation approach, where step by step, it increases the resonance of that VSD to match the baseline production, and sees whether there is a temperature which is being triggered is stabilized or not. Okay, that temperature increase can be due to sand, which is momentarily produced. So once the temperature is stabilized, it automatically tries to maintain the speed and try to see if the production is increased. So if you see, even if you maintain the speed and the temperature is going down because the sand production is now less, then it comes back to your initial production. And then sometimes is go back and the processes keeps on repeating. So this is the scenario in case of insufficient lift and recovery in a real-time example, the screenshot which we given me. Startup, which is another highest risk of ESP failure, which we just discussed. Here, two things are very important. Time to detect that startup. So x-axis is your time in minutes and y-axis is your frequency. The same thing we are checking with choke and same thing we are checking with current. Remember the data analogy, we don't rely on one set of parameter. We have to cross check with the other set of parameter to make a correlation, right? So what is happening here? How do we avoid a startup failure of an ESP? So first of all, currently the challenge is it's very manual process. Okay, we detect and check it and then we react. And that reaction time can vary significantly from 5 minutes, 10 minutes to hours to sometimes several hours, right? So fast reaction time is very important because as you rightly said, ESP fail during startup the most, 80 to 90%. So we need to detect any anomaly within minutes to avoid ESP failure and potential permanent damage to the ESP, right? Because this is where your motor gets permanent magnetic motor gets hit, right? And then surface operation constraint, reservoir related issues, and finally and most importantly, you need to advise, can we devise a startup process that protects both the well and ESP, because it's not ESP, sometimes it's related to well. Okay, so how do you do that? So first of all, you need to ensure you detect it within certain time frame. You could not afford to allow the ESP to run for a certain time and then all of a sudden you fail, right? And then the electrical signature, the harmonics, it is coming. So let's take a deep dive how the automation using model prediction can avoid such high risk ESP failure during startup. So this is the model prediction, which we call MPC, model predictive control. So this is an action coming from the artificial intelligence tool, which is a physics-based model, and it has a combination of a mathematical model as well, right? Which really gives, not only predicts, but it also gives you control capability to maneuver that dangerous period of startup. Okay, the capability of allowing control to multiple constraints using models such as digital twin. Okay, you can apply it to many problems, not only to startup. So the MPC finds the operational control action also from the model, that is multi-input, multi-output system, which is reinforced by machine learning. So what is happening? Let's take a look into it. So the first curve is the pump speed, and the second curve is for the choke opening. Okay, I have to apologize again for my granular graph. I should have increased the size of the graph. And here, this is the pump curve, how the ESP pump behaves. So you start up, all of a sudden, the pump speed goes slowly increases, and then it goes beyond your operational limit. And that is where you tend to control. First, you need to detect very fast and then try to control. So what it does, the model predictive control, is actually it detects all the speed, remember that temperature, pressure, and it analyzes that and sees whether it is going beyond that band. So this band is already predefined. Why it is predefined? Because Schlumberger, because of the pedigree of ESP pump from Kudu, from different OEM, we know exactly where should this pump operate. This is the ideal band. You see this dotted line? So within this rectangle, it should operate. It should not go beyond this and beyond that, right? So the moment the speed of the motor increases, automatically the motor predictive control adjusts the choke. By adjusting the choke and VSD, it brings back to the operating envelope. And that is where it is so important to detect it fast. So if you see, within 10 minutes, it detects. Actually within 1.5 to 2 minutes, it detects and then started bringing it back to the operating envelope. If you do not do this automatically, physically for an operator to save your ESP at a remote well site or a platform is impossible. So you lose money on this ESP, you lose money on the well, you lose money because of the production loss. That is the beautiful thing about the model predictive control, which we can bring in to this. Okay. Now you must be wondering, okay, Schlumberger has this card or the best efficiency point, right? Or for any pump manufacturer, you need to have this best efficiency point. So all you do is controlling that action and minimize your pump off situation or your overspeed situation or gas lock situation. That is where the recommended operating range for MPC startup is coming into picture. Whereas for manual, it is virtually impossible to take action within short time, right? This is again another MPC for ESP startup where you can see it's been stabilizing fast. One of the things is controlling back. Another thing is stabilizing fast. The stabilizing fast is achieved because you know all the surface parameter. You could tune your speed and choke to meet it fast. Okay, so in a way you are directing the ESP saying this is where you should be at. If you don't have this, imagine if you don't have any direction to the ESP will behave whatever it wants to be. So in a way, the MPC acts as a target set point for your pump to behave. So that way you could not only achieve your production, but also achieve enhanced pump life. Because if you are not overrunning the pump, if you are not overspeeding the pump, and if you are facing sand issues, gas lock issues, and successfully mitigating that, what you are doing? You are increasing the pump life. If you are increasing the pump life, that is giving you production and also less workover and maintenance. Now, the AiRP can be different to different customer. And believe it or not, many countries has different perspective to see. Some countries sees electrical power as major issue. Example, Australia. They see electrical power can be very, very critical to minimize ESP's consumption, right? Because availability in power in some of the remote site is minimal. Some customers sees maximize production as the most important criteria. And some customer, or in fact, most customer, would like to protect the ESP from failure, from maintenance, okay? So the MPC is more than a basic closed loop control. What it does, basically, you can fine tune your preference and the triangle and make it as per your wish. Like if you want the MPC to focus on production, it will focus on production, but it will same time keep an eye on your ESP failures and control performance. If you want to keep an eye on electrical power, it can do that with your own priority. It addresses all of those, but you can also, depending on your KPI, production capabilities from certain good wells, you can vary it accordingly. And that can be done either on a field wise, that can be done across the asset or with respect to specific wells. This is one more beautiful thing about the MPC cost function. Now let's see gas lock situation. I think after this, I have one or two more slides and then we'll take questions. So the gas lock mitigation measure is also very crucial. Okay, like startup, gas lock can be catastrophic. So the objective here is to develop algorithm to mitigate gas lock situation and automatically recover to normal position. That is important. Only by detecting, giving alarms doesn't really help in today's time when our workforce are highly changing. Either they are transferred, organizational changes, training, we can't train them properly, new hires, a change in department, you never know, right? So these systems really complements clients or our customers to build up those gaps between competency, maintenance, and production. Because if we can't bridge the gap of competency and maintenance, we can't eventually get into those production objectives. So it's very important to understand how this technology is trying to mitigate both the competency issue as well as the maintenance. So the solution which we are offering in case of gas lock is basically, if you see there is a gas lock condition here, if you see in the 3D analysis, this is the same thing. You have a split problem because of gas lock. So what it does basically, the system is it measures your model through multiple dynamics, again the electrical signature, etc., etc. And then what it does, it creates a digital twin. A digital twin means when you see this representation of the 3D analysis of your actual data, which is coming from the field, from the pump, it checks back how much I need to stabilize in order to mitigate that gas lock situation. Stabilize in terms of my frequency and speed and discharge pressure. Okay, so for example, if you see, it checks series of field tests virtually in a virtual platform. It checks the gas volume fraction, okay, and ensures the flow scenarios. So first it tests itself from a insufficient flow towards a more of a stable flow, and then it checks towards more of a stable production flow, and it takes the data from your particular ESP or the particular well and simulate that into a digital twin environment where a multi-phase performance is mapped and checked. Once this is checked and validated that yes, this should be the frequency, speed, and and the pressure, then that has been written back to the field from the engine so that the gas lock condition which you see here is avoided. So this is a true benefit of a digital twin where you are simulating your actual condition and checking, the engine is checking, and then writing it back to avoid the wellbore analysis. So this is kind of a mimicking. You are mimicking the ESP wellbore dynamics in a laboratory flow loop. Here you see, this is your laboratory flow loop, and this is your actual flow loop. And once you are reaching to a conclusion on a laboratory flow loop, and you can do that with your petroleum domain. You say, okay, the engine is giving me, let me take a look at it. You can take a look at it also, whether whatever engine is doing is making sense. But by the time the gas lock could cause damage, okay? So here the advantage of the system is the system itself is preventing the gas lock, okay? And later the engineer can sit down and analyze, okay, this is what has been done. And I think this could be a best practice we can implement for rest of the well. And now that becomes a benchmark for all our well. So this is the way the human and machine or the digital twin can work together to complement each other. I think I got a couple of more slides and then we are good for questions. So the digital avatar, this is what is the final picture we want to see. First, we want to take the well configuration and pump configuration from the fixed input. Then we want to take the electrical signature, either it is a water cut or GOR, current, voltage, frequency, vibration, okay? Then that goes to offline physical model, which in turn, we advance it through the machine learning, what you see. So from the AED, we get into the model predictive control part. And then finally, through the digital avatar, we can take decisive action towards your ESP surveillance system. And in all these pieces, both the physical parameter of the well equipment signatures are taken, and also you can interface the Schlumberger petrotechnical connectors such as PipeSim, Olga, ECS to make sure all these exercise which we have been doing has a valid business impact to your ESP reduced order model. So let's say if you don't have subsurface, we can use PipeSim, steady state, or maybe Olga, transient analysis to model that in a digital space. And again, that mimicking thing comes. So you don't have downhole gauges, for example, and you have, let's say, ESP surveillance system running due to some reason. So we can simulate your completions to mimic that and still able to give you the same performance, almost similar level of performance. That is the true value of Schlumberger and Sensia here, bringing the technology piece and the optimization piece together. Okay, so I think I also need to highlight these critical attributes. So the final attribute could relate to GOR, efficiency, pump and wear and tear, where it is right now very difficult to access, right? So this system also addresses those maintenance related capabilities and efficiency of the pump as well. With that, we come to the conclusion. So capability for complex physical based model defined for a specific scope to be broadly operationalized for automation. It can be applied to many problems, as you can see, right? And mainly the problems could cause from various physical properties of the well, as well as issues with the physical pump itself. It provides derived measure output that would not otherwise be measurable, right? This is why this is so important. It provides ability to do what if scenarios. If I could not decrease the speed, what would happen? So those scenarios you can get at the back of the site. Ability to perform auto calibration with external source and measurement. You see the data quality issue, how that has been interpolated, how the gas lock issues have been interpolated. Defined based on model and available inputs measurement can also be a guideline to demonstrate benefits of sensors. I didn't cover many of the examples, which is virtual flow measurement we can do with the same engine. We can do equipment-based model conditioning, monitoring, failure prediction. Of course, we covered that briefly, but there are much more into it. Also, gas lift and rod pump we can do in this. If you are interested for gas lift and rod pump, we can take next session where very similar technology, same platform. You don't have to go for another platform. The beauty of this is the platform remains the same for ESP, SRP, PCP, and gas lift. It's a common platform. Only the engines are different. Here we are using AiRP, artificial intelligence response prioritization. In gas lift, we'll be using a calculation engine. In rod pump, we'll be using a pattern recognition. So if you have more time, maybe we'll deliberate that into the next session. But the main fact here is you don't have to train your people separately because it's the same platform. The visualization is consistent. The interface with Schlumberger systems is very, very much there because we have done that integration quite well. And then the final outcome is it boosts your production, especially in brownfield, where your ESP pumps are there for many years. You have cost saving because of reducing downtime. If your pump is not failing, your production is not falling, therefore the downtime is minimum. You are also cutting down on emission because you are not traveling to the site to take these actions. These actions are taken by themselves by automating the workflow. And instead of hours and days, you are optimizing your wells the other way around. Instead of weeks or days, you are optimizing it in hours. That's the beauty. So you are getting instant production increase because of the automated workflow. Okay. So we are taking you from a slow loop decision making to an extreme fast loop decision making where you can impact your KPI. Okay. And then finally, the cost of recovery or the ROI. if you take a look at high GOR well, an operator expects to gain about 400,000 barrels per year. That is what is possible. And we have a SP paper we can share where we have shown them incremental production up to 1,095 barrels per day per well over a one period of time after deployment of this platform. And more importantly, very negligible issues such as gas lock, which we cannot do through manual intervention, right? It is completely automated. I think with that, we would like to thank you for your patience listening, and we would stop here and take any of your questions if you have. Thank you very much.
Okay, well, thank you very much for Mr. Misra for such interesting and attractive material to be given to us. So next, we will head to the Q&A sessions. And as I explained before, you may ask your questions directly to the speakers by turning on your microphone, but first using the right hand feature. And then after mentioned by me, you can turn on the microphone and ask the question directly to the speaker. But if you have a problems with the microphones, you may use the chat box column to state your question, and I will read your question to the speaker. So for starting the question and answer sessions, if there is any of you want to ask, you may ask your questions to the speaker. Maybe for the first, Mr. Eki, you would like to ask your questions directly, maybe? Okay. Okay, I will read the question for Mr. Eki. So the question is, what kind of applications and or systems that you use to manage the communication between the data and application in the back end? Do you have any special transfer protocol while managing the data integration to get the automated analysis? That's the question, sir, Mr. Misra.
Yeah, I think this is a very good question. First of all, thank you for this, because you have really asked a very infrastructural domain question. So this is a surveillance platform. If you remember, we discussed in the beginning, this can be run either on the cloud or on the on-prem. So the way it communicates between the site and the platform is based on either a radio communication, standard radio, or satellite communication, or it can be GPRS or GSM modem, right? And that is standard. If you see Indonesia land, most of them are already there. Offshore could be with the satellite. So to answer your question, what we do is we either provide an edge RTU at the well pad or the IoT device, which can take all this data, both the wellbore data, also the equipment data such as VSD and pump data, downhole and surface. And then that IoT gateway will ingest that data to the cloud, or if not cloud, then through the communication channel, which we just discussed. It will come to a workstation or a server, which can be at your petrotechnical domain or a SCADA domain server on-prem installation, and then and the system works. So the most important thing here is the data backfilling. So this surveillance system runs on a connected production platform, the AiRP, which is now known as Omni Surveillance System. So what it does, the IoT gateway, which we install at WellPad, which is pushing this data to connected production, or the AiRP system, is work on a protocol called MQTT, or Message Queuing Transfer Technique. So the MQTT protocol actually backfills all your data. For example, if you have a communication loss, right, due to line of sight or due to various reasons, then ultimately you're losing data. So what it does basically, once the communication comes back, our data is timestamped, so you're not losing data. So the data is stored on the edge of the IoT device, and then from the archive memory of the IoT, immediately that gets transferred to either a cloud or to an on-prem AiRP platform. And on that AiRP platform, it is immediately been actioned, and again that action comes to the well pad, certainly to take care of that preventive, control, whatever it depending on the outcome of the AiRP engine. So this is, the answer to your question, if that helps.
Hello, good afternoon, Mr. Misra.
Good afternoon, sir.
Yeah, it's Justian speaking from Petrolink. So what you are trying to say is the MQTT will enable the data. I mean, once it has a communication issue, and once it's resolved, the data will be backfilled automatically, something like that, right?
Correct.
So how long will it be fixed? I mean, any time frame, like is it in 5 minutes or 10 minutes, something like that?
It depends on what is that downtime of the communication. Let's say if you have a downtime of 30 minutes or 20 minutes, obviously the backfilling won't take much time, right? Because the data size to backfill is limited. But let's say if you have a downtime of 1 day or 24 hours, then the data size which need to be synchronized is quite high. So then it would take a prolonged time. And then another factor is the communication speed between or the bandwidth of between the host and that. Again, we don't need much bandwidth, to be honest, because all these data are being simple text data. We don't have a rich format as such. Therefore, we don't need much bandwidth. So the predominant factor to time is how much is your downtime. If your downtime is short, it is momentarily, then don't worry about too much. However, if there is a major failure, such as a cyclone has gone and you have mobile towers down or radio towers down, then obviously you can't help it. It's a catastrophic impact. But if it is a relatively low loss of signal, like mobile network is out for 5 minutes, 10 minutes, or half an hour, don't worry. It is designed to take care about those problems.
All right. So during the time frame of the issue, let's say we have an issue with the communication, so the data cannot be transmitted. What kind of business continuity plan you have? So if we lost the data, it will affect the interpretation of the system, right? So what do you think?
Yeah, so and this is a very good question again, because 90% of the time, this is again related to permutation combination. When do you see such situation? Can this happen? Yes, this can happen. If you have a communication loss and something happens, then you are dependent on the decision from the engine on the cloud. But if it is on the cloud, it's less issue because some way or the other, the reliability of the communication would be much more enhancer. In case of major issue, if you have a catastrophic failure, then definitely what the system does, it resets itself from the edge layer. And this is where we are enhancing the platform, where we have Schlumberger edge computing come into picture, where we can interface that with the device, where you can run the algorithm in the edge itself, right? So you have two-stage approach, one-stage approach with AiRP, holistic approach, where it manages your entire workflow. And the second approach would be the edge gateway approach, where you have some backup ESP algorithm where you can mitigate that in case of communication failure. But the question is, do you need both or do you need one to start with? That is where we need to really sit down with specifically with you and understand what is the actual need for that, But to answer your question, yes, we have edge platform to mitigate that communication loss, which can be hours or days.
All right. I think it's enough. Thank you so much for the answer. Thank you, Ode.
Okay, thank you, Mr. Eki, for the questions. And next, we have a raised hand from the participant, which is the Mr. Tony Brito, our speaker today. So, Mr. Tony, please go on.
Yes, I'm so sorry. I had so many communication problem here where I am. Was expecting to be in a different quality. To complement what Devasis was mentioning, right, and I think he answered it properly. What we are looking for is to have some sort of what we call a gateway, an internet gateway that will buffer the data. So you will store the data there for even 1 or 2 days, right, locally in the well or in the field. And then we also have in the platform we have a multi-node data repository that is also high available. So if you lose nodes of the data repository, you still can continue working with the other 2 nodes as the data replicates when we write into the data repository. So to complement what Devasis mentioned, it's a 2-pronged approach here. Thanks.
Thank you, Tony, and thanks to managed to join this call. I mean, it's very good.
Okay, thank you, Mr. Tony. And next, we have a questions from Mr. Julianta. And Mr. Julianta, you want to ask directly? Maybe?
Yes, okay, thank you, Bang Ode. Misra or Tony, in case of gas block mitigation, the case study that you shown to us, how much the efficiency that we can get? And do we have any real case applied in any particular field worldwide?
Sorry, sir, what's the second part of the question? Can you repeat for us?
Do we have any case applied in any particular field? It is the common strategy nowadays, or it is still a conceptual thinking?
Okay, so the question is whether we have deployed this solution in commercial application and what is the best practice around this surveillance across the world, right, sir? Is that what you're asking?
Yeah, so it's like how much the efficiency that we can give before and after, and then how do we have any real case applied, or this is still in a conceptual or fundamental thinking? Thank you.
No, that's fair. That's fair question. First of all, maybe Tony would answer most of it. I can only say that this system is not conceptual. As you can see, this is a deployed system in most of the surveillance piece, where we are having migration from conventional platform, surveillance platform, where it is monitored from 2 to 10 stops with multiple screens. And as you hear during the presentation, training and domain expertise, COVID issues are leading to success of this platform. So to answer your question, yes, we have deployed. We can share the reference with you if you want, some of the reference for this particular piece. And I think Tony can answer more on the efficiency side.
Yes, thanks, Devasis. There is a good use case that we documented recently, actually with the support from the customer. And they managed to identify the different type of conditions of the pump related to gas lock, related to low flow, etc., problems with torque. And what they managed to do was to extend the life of the pump around and reduce the deferred production more than 10%. So in terms of efficiency, the system allows an early detection of the conditions automatically. That's one of the part of the value that we're trying to bring in, and then take action to avoid the premature failure and before the normal wear and tear kicks in, right? We are, according to the study, the guys in Latin America, they managed to extend the life of the pump in a few months and reduce the workover cost as well. So there was a two-side benefit there in the project. We can share that reference as well separately.
Yeah, I'm sorry not able to cover the reference. I think we should have done one slide on the reference. But anyways, if you can share your mail ID or the organizer can share their mail ID, Bunovi from Schlumberger will share these references with you, sir.
Okay, thanks, Mr. Anthony.
Okay, thank you, Mr. Julianta, for the questions. Okay, maybe for the next questions, if there is any one of you want to ask the question regarding the material that already has given by the speaker, you might ask your questions directly by turn on your microphone, or you might just text the questions and I will write the question to the speaker. Okay, there is a request for asking the questions for Mr. Salis. You may unmute and turn on your microphone. Mr. Salis, are you here?
Yes.
Oh, yeah, okay.
What's the question? I don't.
Did you have questions for the speaker?
No, not.
Oh, sorry, Mas. Okay. There is a questions from Mr. Dika Putra. Please go on.
Okay, thank you. Mr. Misra, I'm just wondering about the system of VSD in this, how can I say, ASP. Is there any, how can I say, relationship with the transformer setting in the platform? Because sometimes if the, how can I say, if the setting of VSD is beyond the transformer capability, we need to change the transformer as well. Thank you.
Okay, so the question is whether the transformer has anything to do with the surveillance piece, more or less, right? That's the question.
Yes, correct, exactly. Yeah.
Okay, so if you see the diagnostic which we are taking from the equipment and the well level, these are predominantly electrical signature and surface equipments, health and their operational parameter. So if you look at the transformer information, that could not be a direct information. It could be indirect information, meaning if you have issues with the transformer, then eventually you will see the anomaly in the power quality, right? So to answer your question, we may not take a direct transformer exclusive like sort of input, but the byproduct of a transformer such as current, voltage, frequency, harmonics, we do take care. And that is where the total harmonics distortion or THD comes into play, where we continuously monitor the distortion which is coming from the transformer, right? So hope this answers your question, right?
Yeah. Because in my experience in the past, when we make VSD, we have to setting the transformer with the, how can I say, width, how can I say, width of range VSD as well. Just follow the how far the VSD can set
and go. Yeah, correct.
Like
yeah. So this is the TSD coming from that. Now I am getting your question. You are asking about the electrical properties of the transformer, not as a physical transformer. So the answer is yes, we do.
Okay, that's good.
Yeah.
Thank you, Mr.
Thank you, sir. Tony, you would like to add anything on this one?
Yeah, also the system, right, has an ability to to combine with the power signals and also to create some sort of profile of power consumption versus operational levels, right? And we have created some dashboards and some applications in South America as well for that can also be shared. So it's not only for diagnostics of the performance of the lifting system as such, but also can be related or can be correlated with the performance of the electrical equipment in the surface, specifically consumption and performance of harmonics, etc. No?
Yes. Yeah. Yes, Tony. Mm-hmm.
Thanks.
Okay, thank you for the question. Maybe due to the limit time, we have just one question again before we end the session of the Q&A. If there is any from you want to ask your questions, please go on. Maybe if there is no questions anymore, we can have we can request the feedback from Mr. Salis maybe, because Mr. Salis is already in the digital field for a long time. Maybe we can have feedback from the Mr. Salis regarding this topic. Mr. Salis?
Okay, thank you. Very good presentation. I think it is excited presentation. And I hope this can be implemented in our field, because you know that ESP, there's many fields that we have ESP for artificial lift. And later on, I think the next session about SRP and PCP and other artificial lift will be very good to share with us. And then I think I want to underline here that ESP that we install in this field has to be installed the sensor, right, Mishra? The sensor, not all the ASP that we can take it as an automation, but we have to put the sensor either in the ESP itself and in the flow line and until the in the production line to control the production and optimize this system. When I present this in SPE, I also talk about what I call IPMOS, the Intelligent Production Monitoring and Optimization. So not only monitor, but optimize the production. And this is kind of different kind of tools that very good monitor and also optimization from the ESP, from artificial lift. And later on, we will learn about the ESRP and PCP. Again, thank you for sharing this new technology for the digital. And I believe this will be more and more familiar with our engineers, not to replace engineer, but to complement these tools. So engineer will easier to analyze, focus on what the root cause and what is the thing that we have to optimize. That I think the ultimate goal of this kind of tools, because the technology is only tool, but behind that the people still important to analyze and to make a decision. So thank you so much for collaborating even from IATMI and IAGI and ISPG. And thank you so much for the speaker. Have a good day. Thank you.
Yeah, thank you, sir. Thank you, Pa Salis. Pa, if you have half a minute, maybe Tony and myself have just a couple of questions, if you don't mind, before we wrap up. Yeah.
Sure.
Yeah. So I hope you see there is a value in it. But in case of actual deployment, do you have any opportunity where Schlumberger and ourselves can have established this technology and show you the outcome? Because there was a question on where we did it. I think Indonesia, we are starting off. Can we request the fraternity here to come back to Bu Novi or and Schlumberger so that we can help you deploy somewhere if you are facing this production challenge or the gas log or the ESP failure issues, etc., etc.
Yes, actually, yeah. Now I'm already retired, and and then I see many opportunities here, because many field that using ASP, and from Schlumberger, I think you have a lot of data that which one they already been installed, the sensor of special ESP. I don't know. At the time, I collaborate with ZDI, and ZDI product is already been used in Schlumberger. So yeah, by looking at the data that which Schlumberger that already supplied the ESP, I think start from there. You can implement or maybe try to the entering the field, and I think more than 10 fields that already use many ESP, and we can to support that Pak Hadi Ismoyo as IATMI proposed the 1 million target of production, and then it can boost the production there without any downtime. That's many downtime now, or especially for ESP.
Yeah, if you have any field where you really wanted us, we will be more than happy. And just to let you know, the JEDI platform which Schlumberger used to use, actually that's now within Sensia. And that is where this improvement we have done with AiRP actually. So it's just not a platform to give you surveillance. Now it provides and complement the engineer with some preventive action, eventually impacts either your downtime or production. So this is, the 4.0 version, industry version we are seeing, which is much more higher than the JEDI platform.
Yeah.
Yeah. I think Tony might have some question, maybe due to lack of time. Tony, please go ahead.
No, I'm fine. Thank you for the opportunity. I would like to appreciate all these opportunities and the efforts, and really apologize for what happened in terms of the connectivity. But well, I think it went very well, and we're ready to support further into clarifying questions and providing demos and even proof of concept if required. We have a program for proof of concept of the platform, very affordable, and also can help to be deployed very quickly, especially if it is on the cloud for proof of concept of pilots. And we have demonstrated the benefits of such connected production and surveillance in several places already, and the success is very good.
Okay, I think that's it from our side, sir.
All right. Good. Very good.
Okay. Thank you very much for Mr. Salis and our speaker today, Mr. Mirza and Mr. Tony. I think we are very sorry due to the limit time. We already in the end of Q&A sessions. And before that, I have announcement for all the questioners in this session. Need to contact the committee because we already prepared the present for all the questioners. days. And then before we end this event, we would like to say thank you very much again to the speaker for having such a good material given to us here in this afternoon. And then thank you very much also for the interesting by the all participants today. And to end this event, maybe I would like to give back to the host.
Yeah. Thank you, Bang Ode and all participants. Kindly please open the camera so we can take picture together. Bang Ode will try to help to snapshot.
Yeah, sure. Okay, please, all the participants, maybe you can turn on your camera for a while we have photo sessions. Okay, I think the photo session will start. I will lead the photo session. I will count on 3, 2, 1 and take a picture. Okay. All right. 3, 2, 1 and please. Okay. The first take is already. Maybe for the second take. If you okay. All right. For the 3, 2, 1 and go. Okay. The photo is already taken. Sorry.
Thank you.
Okay, thank you, Mas Ode, as a moderator, and Mr. Tony and Mr. Misra. Thanks again for your willingness to share the knowledge with us. See you to all participants.
Thank you,
in the
sir.
next
Thank you very much.
ISPG and IATMI, another collaboration meeting. See you guys.
Okay, thank you.
Be safe and
Thank you very much.
Thank you. Thank you.
thank you.
Thank you.
Thank you for host.